Good evening, everyone. Welcome to the sixth interactive session of circular dichroism and Mossbauer spectroscopy. My name is Tanu, and this is a sixth interactive session on circular dichroism. So far we have already discussed about the importance of chirality, how to find out the optical activity, what is plane polarized light, circularly polarized light, point group symmetry. We have gone through a lot of topics, but today we will be mainly focusing on the applications of circular dichroism. I will be summarizing some important points on circular dichroism, like its instrumentation principle and what is its importance. So uh, these are some of the topics we will be discussing today, and so we will start at 6:05 if someone has to join till then. Okay, so let's get started with our today's session. So as we know, light is an electromagnetic radiation with its electric field vector and magnetic field vector perpendicularly associated with each other. So now if we look into this electric field vector, because magnetic field is a weak force, magnetic field is a weak field. So if we look into this effect of this electric field, it follows a sinusoidal wave function. So with any light, this electric field vector and magnetic field vector is always associated. And this light consists of different electric field vectors being oscillating in every possible direction. That is, this is unpolarized light with its vibrations in all possible directions. So if this unpolarized light is passed through a polarizer, polarizer is generally a crystal which allows only a single plane which allows only a single plane of light to pass through it, then we will get a plane polarized light. That is the light which has its oscillations in only one plane. Now this plane polarized light, when passed through a chiral molecule, this chiral molecule can rotate the plane polarized light at a certain angle with respect to its initial position, and the angle at which it is rotated is called optical rotation angle. So now this chiral molecule has some enantiomers. Enantiomer A, enantiomer B, such that this enantiomer A rotates the light anti-clockwise. That is, and this enantiomer B rotates the light clockwise, clockwise. So the chiral environment can detect the chiral molecule. So if we have an unknown sample and we see that the light coming out of of that sample is rotated at a certain angle, then we can say that this unknown sample possesses chirality, and if not, then it will be a chiral. So here, this plane polarized light, this plane polarized light, as we know, since this linearly polarized light is the light with oscillations confined to single plane, as we have already discussed. So if we have if we have a circularly polarized light which consists of two perpendicular electromagnetic plane waves of equal amplitude, but at 90 degree but at a 90 degree to but at 90 degree associated with each other, that is, there is a phase difference of 90 degree. So here we have two plane polarized lights which are aligned at 90 degree with respect to each other, that is, they are perpendicular to each other. So so when this plane polarized light consists of two two parts. One is right hand circularly polarized light, and other is left hand circularly polarized light. And the superposition of this right hand circularly polarized light and left hand circularly polarized light gives us a linearly polarized light. So when these two parts are superimposed such that we get this type of polarized light, then we can call it plane polarized light. But if there is an angle difference and that is 90 degree, we call it a circularly polarized light. So, circularly polarized consists of two perpendicular electromagnetic plane waves of equal magnitude and 90-degree difference in phase. And these right hand circularly polarized light and left hand circularly polarized light are non superimposable, such that chiral molecules can detect the difference between these two lights. So now there can be two cases. One is that these RCP, right hand circularly polarized light, and left hand circularly polarized, are moving at different speeds through the media, that is the sample we have taken, chiral or achiral, whatever it is. And and the other case is differential absorption of this right hand circularly polarized light and left hand circularly polarized light by the sample. So this effect is what we call, this is optical rotation, and the effect produced is called circular bi birefringence. We have already discussed these things in the last lecture, but it's just a summary of what we have read because it will help you to follow up whatever we will be discussing about circular dichroism in details. And it depends on the, so the parameter affecting this is speed of light, and this speed of light, this optical rotation, is directly proportional to the refractive index. The different speeds, so this depends on the refractive index of the sample. So due to the difference in the refractive index, like we have one sample, so it has its refractive index of its own. So with the incoming light which is falling on this sample, it will be differentially interacting with this with the sample, so that the one of the enantiomer um we can say the left hand circularly polarized light can interact, can pass at a faster speed than the right hand circular polarized light. So there are the different speeds through which these two type of lights will be passing through the sample. And so for a fixed concentration, this optical rotation at a particular wavelength and temperature will be equivalent to uh, optical rotation of the sample, then the concentration and path length of the sample. So this will be the formula. Now coming to this differential absorption of right hand circularly polarized light and left hand circularly polarized light. So the phenomena which is taking place here is this is the phenomena which is taking place, and here it is ellipticity. So right hand RCP and LCP can be absorbed in different ratios such that we end up getting an ellipse. So the effect here is circular dichroism. And the this psi, that is the difference in absorption, will be defined by tangent psi equal to differences in absorbance by left hand circularly polarized light and right hand circularly polarized light. So we have two phenomenons here. One is like we have two phenomenons. One is optical rotation, which we call optical rotatory distortion, and the second one is circular dichroism. So one depends on the speed of light, and the another depends on the absorbance of a particularly polarized light. So both of these phenomena can take place together. So plain polarized light, superposition of the RCP and LCP. So this circularly polarized light wave can rotate in one of the two possible ways, that is clockwise, what we call right-handed circular polarization, in which the electric field vector rotates in the right hand sense, with respect to the direction of propagation, and counterclockwise, or which we call left hand circularly polarized light. So it is shown here. So you can observe. So so this is moving like this. This is anti-clockwise here with respect to source. Like in my respect, it is anti-clockwise, but from the respect of viewer, that is you it will be clockwise. And this, from the point of view of viewer, it is clockwise, and this clockwise rotation is what we call right hand circularly polarized light. Okay, and this right hand circularly polarized light is associated at 90-degree angle with respect to the direction of propagation of the uh, electric field wave. So there are two waves. One is moving uh, parallel to the one is moving perpendicular to the direction of propagation. So this is direction of propagation, and this light is moving at 90-degree angle with respect to this direction of propagation, and the direction of and the direction of rotation in this case is right hand, that is clockwise or clockwise rotation. Similarly, in this case, with respect to the like with with respect to me, it is moving anti-clockwise, and this will be left hand circularly polarized light. So you can see that these are 90-degree with respect to each other. Okay, so this was the point I wanted to convey. And the circular dichroism, which is the main highlight of our today's lecture. So it is the differential absorption of right hand and left hand circularly polarized light by an active molecule, by an active molecule. So that we have already discussed, like what type of the molecules will be called CD active, and I will be summarizing it again today. So this origin of optical activity is dependent on the transition moment integral which defines nothing but the probability of transition of electrons from its ground state to excited state. So, this if we call reaction coordinate, and this is energy axis. So, if we have an electron in ground state, and we have a molecule in ground state, and we radiate it with a plane polarized light, so what would be the possibility, what would be the cases this molecule will go to excited state? So a chiral molecule, if we induce, if we want to induce the optical activity in a particular molecule, there would be three factors which will be involved for this transition, so that the light is absorbed, and the optical rotation, or this absorption of right hand circularly polarized light and left hand circularly polarized light will take place. So it is defined by this transition moment integral, and this operator, this is basically the perturbation we will be introducing here, which is dipole moment operator, the change we will be inducing. So we have already discussed that there are electric field, electric dipole moment, mu e, magnetic dipole moment, which is a weak effect because magnetic field is a weak field with respect to electric field. And third is electrical quadrupole moment, which has almost negligible value, which like induces negligible effect in this transition. So mainly we will be discussing this electric and magnetic dipole moment. So as we know, this electric dipole moment operates along position vector. Electrical dipole moment interacts along position vector, that is x, y and g axis, that is along a line, that is electric dipole moment interacts along a line. But this magnetic dipole moment is a cross product of position vector and momentum vector, which means it operates perpendicular to the position vector and moves in a circular plane, or we can say move or interacts in a circular plane, circular way. That is, if this is electric field vector, then magnetic field vector will be associated perpendicular to it and moving in a circular manner. That is, this is magnetic field vector. So these two are the main highlight here. Now, this electric field vector impacts the absorbance by a sample. That is, we can say absorbance is only dependent on the electric field vector. If we write this Beers-Lambert's law, where epsilon is the molar extinction coefficient, an intrinsic molecular property, that is, for every sample this extinction coefficient will be different because of different oscillatory motions. But in cases where this electric field vector and this magnetic field vector both are active, so if we have taken a molecule and if we are recording an absorbance spectra of a molecule, and we say we are getting some peaks in the sample, so we can't define whether this molecule is chiral or achiral, as in this case only electric field vector is involved. But in the cases where electric field vector and magnetic field vector both are active, and if we record a spectra for that, and the spectra is what we call is CD spectra, this is where we can define whether particular molecule is chiral or achiral. So, so mu m is associated with the rotatory strength of the molecule, and this electric field vector was associated with the oscillatory strength of the molecule. With rotational strength, if we say correctly. So mu, the cases where both electric field and magnetic field are active, in that case we call it rotatory strength. So when we have this electric dipole moment and magnetic dipole moment, both are active. Magnetic dipole moment, both are active. So this moves in a linear manner and this in a circular manner. So now the cases where both are active systems, where both are active, The resultant motion will be helical motion. Depending on the direction of operation of this electric field vector and magnetic electric dipole moment and magnetic dipole moment. So the resultant motion will be helical motion. So if we have this right hand circularly polarized light and left hand circularly polarized light passing through a sample. So if this is optically active sample, in this sample electronic distribution will be such that it can detect it can excite both electric and magnetic dipole moment of the molecule together. So only the optically active samples will have electronic distributions such that it can excite both of its electric dipole moment and magnetic dipole moment together, and this optically active molecule will be able to detect the helical motion of the right hand and left hand circularly polarized light. So now we have this right hand and left hand circularly polarized light, which are moving at perpendicular, which are moving perpendicular to the uh, direction of wave propagation and rotating at a certain angle with respect to the rotating at 90-degree angle with the direction of wave propagation, and this direction of rotation can be clockwise or anti-clockwise. So the resultant motion we are getting is kind of helical motion. Also in the molecules where in the optical active molecules where both electric dipole moment and magnetic dipole moment are active, there the when these molecules interact with this right hand circularly polarized light and left hand circularly polarized light, because of its manner of electron distribution, it will be able to interact with this pattern of RCP and LCP differentially. So what kind of the molecule are possible? Optically active molecules will have both active, so that their their positional vector and their this rotational axis vector, which is associated uh, perpendicular to the position vector and moving in a circular manner, they will be associated in the same they will be associated, they will be active together. Like if we look into that point group and symmetry we have already studied, so the optically active molecules which we call like cn and dn point groups, so in these two point groups, these only these point groups, cn and dn, have this electric dipole moment and magnetic dipole moment active together, because for their this x and rx, y ry, z and rg are associated with single irreducible representation. So I will be giving an example for that. Chiral molecule will exhibit optical activity, that is rotate the plane polarized light, and it will be mirror image. So so its enantiomers are mirror image of each other but non-superimposable. So the molecules belonging to point group Cn and Dn are optically active as they don't possess a center of symmetry and plane of reflection. So if we take an example, So this is we have to find out the point group for this molecule. So we have already discussed like how to find out the point group. So firstly we have to figure out the different symmetry elements in a molecule. So for example, this is the center of the molecule. So if you see, I have not drawn it properly, but you can just take it. This oxygen are just front of each other, are in just front of each other. So there is a C2 axis passing through this oxygen and the center, this CC bone between two phenyl rings, and also we have a C2 axis perpendicular to this. So now also we have a C2 axis moving out, coming out of plane. So here in this case we have C2 axis as the principal axis, and we have 2C2 perpendicular to this C2. So here we can say that this molecule belongs to D2 point group. So now how can we say that this molecule is optically active? So now let's just look into the character table for this D2 point group. Just a minute, I'm looking for the character table. Okay. Uh, so this is the character table for D2 point group. So in the first column, we write the name of the irreducible representations, which are equal to number of classes in a particular point group. So to know more in details about how do we generate these character tables for a particular point group, what are classes, and how irreducible representations are generated out of it, you can look into the symmetry elements and point group theory videos on my YouTube channel, or you can also follow any NPTEL course on this. So here, then we write the different symmetry elements and we classify them into particular classes based on some properties, or we can say some rules, mathematical rules, which are designed for these character tables. So in one of the column, so in one of the column, we write the linear functions. We can say the coordinates x, uh, position vector, we can say x, y, and g, and rotational functions. And in the next column, we generally write quadratic functions. Here in our case, we are mainly interested in the linear functions. So if we have to check whether a molecule is optically active or not, it is obeying that rule that both electric field and magnetic field vectors are active. That is x rx, y ry, z, and rg both are associated with with the same irreducible representation. Then we can call that molecule optically active. So let's say whether this point group is satisfying this condition or not. So here we have four irreducible representations: A, B1, B2, and B3. So I'm directly writing the linear functions with respect to each irreducible representation. So ZRG belongs to B1 irreducible representation, YRY to B2, and then XRX to B3. So we can say that a position vector and the corresponding rotational vector is associated with the same irreducible representation. So here both the conditions are being satisfied, that is electric field vector and magnetic field vector both are active. So we can say that D2 point group molecule, this molecule is active. This molecule is optically active, and it will detect the uh, difference in speed of that is, it will optically rotate the incoming right hand and left hand circularly polarized light, and also differentially absorb one of them. So now if we have some other molecule, for example we have for example if we have a complex. So here we have octahedral geometry, but we don't have an octahedral symmetry. So in this case, we have we will find out the point group for this molecule. There's a C2 axis of rotation passing through this F molybdenum CO CO bond, and there are two sigma V planes passing through these CO bonds. Sigma V, sigma V. So here we have C2V point group. Okay, so now we have to check whether this C2V point group, this molecule is optically active or not. Although we just have to directly find out whether a molecule belongs to a CN or DN point group, then we can directly say that it is a optically active molecule or not. But just in case, here we are just practicing like how we will be finding out whether a molecule, we're just looking into the details of how a molecule is optically active and not optically inactive. So for CNV point group, if we draw the character table, again here we have these irreducible representations. So we will look into the linear functions and rotational functions with respect to each irreducible representation. So So here we can see that Z, RG, X, RX, Y, RY, these are associated with different irreducible representations. So we can say here either electric field vector is active or magnetic field vector is active with respect to any irreducible representation for this point group. So we can say that both mu E and mu M are not active together. So this molecule is optically inactive. So this is how we can find out. We can look into the optical activity of the molecule. So if we look into the instrumentation for the circular dichroism, so it belongs to it will have a light source. Then we will from this light source we will get an white unpolarized light which will be passed through a monochromator to give us a linearly polarized light. Sorry. Uh, so this monochromator will give you. So white light is basically a light which consists of all wavelengths, right from uh, that is, it consists of all lights in the visible region. So if we pass it through a monochromator, we will get a light of single wavelength. This monochromator will give a light of single wavelength, and this polarizer. So if this single wavelength light, that is monochromatic light, is passed through a polarizer, we will get a plain polarized light. So this linearly polarized light is later passed through a PEM, what we call photoelastic modulator, to produce a circularly polarized light. This photoelastic modulator is used to convert the linearly polarized light into circularly polarized light. So here we will get circularly polarized light, and this circularly polarized light is passed through the unknown sample. So if this sample is chiral, we will get certain peaks in the CD spectra, so which will be identified by the detector. So this is the general instrumentation for a circular dichroism uh, instrument. So now, firstly, we will look into the what kind of CD spectra we get. We get in a circular dichroism instrument, CD spectroscopy, we can say. So for a sample, if we record an absorption spectra in UV visible NIR spectrophotometer, and if we get this absorption spectra, this is optical feature of the sample, the sample. So this absorption spectra doesn't define whether the molecule is chiral or not. And if we record A spectra in optical rotatory distortion spectroscopy. We will, which is like specific optical rotation versus wavelength of the incident light. So this depends on the speed difference in the speed of absorbed light. So here for two different enantiomers, we will get two spectra. If one is rotating, right hand, if one is rotating the incident light in a clockwise direction, we will get a uh, positive absorption spectra for that, and for the other enantiomer we will get a negative absorption spectra. So in this case we will get maximum absorption at the same wavelength, which we are getting the maximum absorption in the absorption spectra. Okay, lambda max. This is optical rotatory dispersion, optical rotatory distortion spectra. This is positive Cotten effect. So, Cotten effect is nothing but when enantiomers exhibit equal and opposite circular dichroism spectra uh, with opposite Cotten effect, that is, they will. So, this Cotten effect is positive in ORD when optical rotation first increases with respect to increase in wavelength, and vice versa for negative Cotten effect. That is, optical absorption decreases with increase in wavelength. If we record a CD spectra, that is, change in absorption with respect to increase in wavelength, that is a difference in absorption by left hand and right hand circularly polarized light with respect to wavelength, is what we call CD spectra. So in CD spectra, we will get peaks only in the region. For example, if we have an absorption spectra, we recorded the absorption spectra, and if we are getting peaks in the same region, for if we are getting peaks in one region and the peaks in other region are absent, peak is absent for this region, then this shows that these absorption peaks are coming because of optically active molecule in the sample. So CD spectroscopy is used to study protein protein structure, that is its primary structure, which is basically the sequence in which different amino acids are present in a chain. So the primary structure is just the sequence in which different amino acids are present in a protein chain, and the secondary structure the secondary structure defines the peptide backbone of the protein chain. That is, for example, if we have different amino acids bound to each other to form this peptide linkage, which is like this COH terminal reacts with the amine terminal of other amino acid to form an amide bond. And this is what forms the backbone of the protein chain, which is we call a peptide backbone or an amide backbone. So this is what we call the secondary structure of protein. And the information on the protein structure is important in finding out how proteins function. And proteins adopt unique conformations such as, for example, which are optimized to perform specific structural, regulatory, or enzymatic functions. So this is very important to find out the primary, secondary, and tertiary quaternary structure of a protein. So this is the structure. So this is the kind of CD spectra we obtain for a protein. The secondary structure, sorry, the primary structure of protein defines the alpha helix structure of protein. And the secondary structure defines the helical structure of the protein, which induces chirality in the molecule. If two alpha helix chains are anti-parallel to each other, actually these alpha helix chains uh, forms bonds with each other to form beta sheets, in which they are associated anti-parallel. They are associated in an anti-parallel and parallel manner with respect to each other. If two alpha helix are anti-parallel to each other, then they form a direct bond. And if they are parallel to each other, that is, if there is an anti-parallel chain, sorry, if there is a parallel chain, then there are skewed bonds between these alpha helix chains, and these beta sheets, or if we say alpha beta sheets, combines together to form the tertiary structure, which is the overall stable structure of the protein. These alpha helix chains form beta sheets, primary structure. These beta sheets together form the tertiary structure, where alpha helix, when associated anti-parallel to each other, they will form beta sheets, and if parallel, it will give rise to random coils. So if we have alpha helix structure, we will get a positive band at 193 nanometer. This is alpha helix structure, where we will get a positive band at 193 nanometer and two negative bands at 218 nanometer and 222 nanometer. So these are signature bands for alpha helix structure, showing the secondary structure of the protein. And for the beta sheets, we will get a positive band with reduced intensity at 195 nanometer and a broad negative band at 218 nanometer. This is, and if we have a protein uh, for which we are getting this kind of peak, that is a negative band, uh, and no peak in the positive side, then it will show the random structure of the protein. So to find out these bands in the CD spectra, we need to record the spectra in the far UV region at wavelengths down to 190 to 170 nanometer. Uh, and the difference in the left and right hand absorbance is very small. Therefore, the CD spectra is generally considered to be sensitive. And this CD spectra is a function of wavelength, that is, the difference in the absorption by right hand and left hand circularly polarized light is recorded with respect to the change in wavelength of the incident light. So again, this when the circularly polarized light passes through an absorbing optically active medium, the speed between right and left polarization differs, as well as their wavelength and extent to which they are absorbed is different. So the speed at which they differ is what we call optical rotation, and the difference in their absorption is what we call a circular dichroism. Uh, for for the difference in their absorption, we record the circular dichroism. So the spectra of two enantiomeric molecules are equal in magnitude and opposite in sign. CD is most used for rapid comparison and characterization of protein secondary structures. It offers a way to determine the effect of a mutation or a change in the environment of a protein, such as temperature change, pH change, ionic strength change, which might affect the overall structure. So, circular dichroism is a very important spectroscopic technique to find out the different structures, differences in the secondary structure of the protein. So I just want to clarify a bit about this primary, secondary, and tertiary structure if there is a confusion. So the primary structure is just the sequence in which the different amino acids are present in a peptide. This peptide backbone, or we can call amide peptide chain of a protein. And the secondary structure consists of four components, that is alpha helical, beta sheet, turn, and this random coil structure. So, if whether to find out whether the secondary structure of the molecule is alpha alpha helix, or it is beta sheet, or it's just a random coil structure, we record the CD spectra. And as I have said, for the alpha helix, we get a positive band at 193 nanometer, and two negative bands at 218 and 222 nanometer. For beta sheet, we will get a positive band at 195 nanometer and a broad band in the negative region at 218 nanometer. And for the random coil structure, if the secondary structure is of random coil type, then we will get a negative band in a lower UV region, that is below 200 nanometer, and there will be no positive band. So So if we have if we have a protein with which have a mixed structure, for example, if we have a CD spectra, so here we can see that we have a positive band. Uh, let's say it is around 193 nanometer, and this is the broad band in the positive region. And here we have two negative bands, but they are broad bands. These are not sharp bends, so we we can't say that this is an alpha helix structure, because here we can say if we deconvolute this spectra, we will get a mixture of so we will get a sharp bend in the positive region and two bends in the negative region. And also a band at a higher wavelength, that is more than this 190, more than this positive band at 193 nanometer, and a broad band in the same region. So by deconvoluting a CD spectra, where we are getting a mixture of bands, we can say that there are different amounts of alpha helix structure or beta sheet structure. So here we can say a mixture of alpha helix and beta sheet structure is present in the protein sample. Also, if we are given a sample for which the structure is changing with a change in pH and temperature, for example, if at pH 5.9 we are getting a positive band and a broad band around 218 nanometer, then we can say that at pH 5.9 we have beta sheet structure. But if this pH is increased, that if we move into a more alkaline pH, this structure changes to this structure, this spectra changes to this, that is two new bands appears in the negative region. So we can say that here at this change pH, the protein structure has changed to alpha helix. So based on different pH and temperature conditions, we can also define how the structure of a protein is changing. So if we have a sample and we change the temperature at which this protein sample is stored and record the CD spectra such that for different temperature conditions we are getting different bands, positive, negative, psi region with respect to wavelength. Then we can say that changes are being induced as a function of temperature, as a function of changes are being induced as a function of temperature, showing the changes from alpha helix to beta sheet or a random coil structure. So I think this was a bit which I wanted to discuss for today's lecture, a summary of week 6 content. Hope this is helpful for you. If you have any doubts or any confusions regarding this lecture, you can post in the discussion forum. Also, let me check whether there are any questions. Uh, so this is it for today's lecture. I hope uh, everything is covered and this lecture was helpful. So these sessions are being recorded, and we are sharing these sessions on YouTube channel. So and the links for which are mentioned in the mentioned mentioned in in each week's content. For example, if you see, so in the problem solving session for like for each week we have this link for the problem solving session, so you can click on this link and you can visit the excel sheet where we are mentioning the link for each recorded session, and also the notes are being shared in the google drive, which the link are also mentioned in this problem solving session tab. So please follow these sessions and write us if you are able to follow the lectures and you are getting your doubts cleared, or if you are facing any difficulties in following these lectures, please write to us. It would be really helpful, and we are looking forward for your feedback. So this is it that I wanted to discuss for today's lecture. I'll wait for like 2-3 minutes more, and then we will end this lecture. Okay. So, writing these values for more clarity. CD spectra of protein, secondary structures. So, alpha helix, we have negative band at 208 nanometer and 222 nanometer. Positive band at 192 nanometer. For beta sheet secondary structure, we get a negative band at 216 nanometer and a positive band at 195 nanometer. These are just the more accurate values I'm mentioning. Then for LH, polypro helix structure, this is just another type of structure reported for the secondary structure of proteins. And for the random coil structure, we get only one negative band at 200 nanometer. So we have this region like 170 nanometer, this far UV region. So for the protein backbone, the CD spectrum is sensitive to secondary structure change. CD spectrum is sensitive to tertiary structure change. For the near UV region, we observe the changes with respect to the tertiary structure change. The secondary structure types we have already discussed. Alpha helix, beta turn, polypyr- polyproline, and random coil structure. And for this, the structural types, we have a like different type of uh, aromatic amino acids, which are phenyl, alanine, tyrosine, tryptophan, and disulfide bonds. So these slides which I'm writing right now are very important. So you can follow these with priority. For example, if I write the confirmation, then the molecular shape with respect to it, and the CD spectrum we obtain for it. If we have an alpha helix hydrogen bonded chain, we will get a helical molecular shape, and the CD spectra will be the values I have already mentioned in the above slide. For the beta sheet, parallel and anti-parallel hydrogen bonded chain. So how these looks, for example, double bond O, NH2, we have NH. If these NH and CO bond are just in front of each other, then we call it anti-parallel structure of the beta sheet. This is the type of structure we get for anti-parallel. Uh, I'll add the sheet for it. I'll add an image for it because there is some. We are out of time now. Just making the structure CD spectra for it. There will be one positive band and a broad negative band. So these are some few. These are few examples. random coil structure, we will get a negative band. So this is it for today. So these are the different CD spectras for different kind of secondary structures. So this is what I wanted to discuss for today's lecture. I hope things are clear for you now. And if you have still any doubts or anything else you want me to discuss, please write in the discussion forum. So, okay. Thank you so much for today's lecture and for your kind attention.